Hello, I'm here at an active site to provide you with a little demo of the Griffin AI Toolkit, and particularly Tabor's offerings of its combustion optimization system and knowledge-based subblowing, or COS and KSB. I'll start here by opening up the Griffin splash screen, give a little introduction to the main areas. The first is data links, where you can control all the interfacing between the DCS or base control system and the Griffin Toolkit. And there's also applications where all the actual logic and calculations are performed. Then there's the models section to interrogate and look at and build neural network regression models and all other types of models available in the toolkit. There's this genetic trainer component, which allows you to optimize and identify the optimal structures of neural networks and other models, data-driven models. And there's a data visualization tab and a About tab to provide some information about the specific install. First, I'll show you a little bit here in the data links. This is again where all of the communication is facilitated between the DCS system and the Griffin server. I can in real time monitor the status of any of these links by simply highlighting the respective link and clicking the view link tags. That shows me the tags within this link, their current status, and then their current values, and you see that these are updating in real time. So this is where you can actually see what information is being communicated between the two systems. Let's go now and look at applications. This really is where the bulk of the work is done by the Griffin systems. You see here each application, the COS, the KSB, and then also some ancillary systems, the model retrainer, data collection system, and some performance calculations. I'll go ahead here and open up the tuning screens of the combustion optimization system. You see immediately pop up a number of trends and tables which allow me to monitor the status of the application. These are all customizable. I've developed each of these by specific request of the operators and engineers on site so that they can look at and see the things that they are interested in. See right here, this is the results of the PSO or particle swarm optimizer compared to the current positions of each parameter. You can see the amount of bias or change that the optimizer is calling for in each parameter. Then over here is a trend of performance of that same model and optimizer. This unit is targeting heat rate. It's actually a multi-objective system heat rate and emissions, particularly NOx emissions. I'm trying to minimize both of those. This plot over here shows the real-time measurement or calculation that Griffin does for heat rate, as well as the model's prediction and the prediction accuracy of the model. You see right here that throughout most of the day there's been some tuning going on of emission systems and other parameters that have had the models a little out of sorts, but once that completed, and then I also had the operators fully engage the Griffin system because part of that tuning had them disengage certain loops. When that was re-engaged here at about 5:30 or so, you see that it took 20 minutes or so for the models to start getting a good representation of the unit, and then over the last hour the heat rate on the units decreased by about 2.5 to 3%. This is really good performance. Typically we observe heat rate improvements in the 1 to 1.5% range. And then also you can see over here the same has been taking place for NOx emission rates. Here the orange is the measured value and the green is the model's prediction. And you see again that once I had the system fully engaged by the operators, that the NOx has been falling out of the unit, it's been being minimized. I'm so very happy to see that. I can also in these screens monitor any parameter that I'm interested in. You can see what load's been doing. The last couple of hours they had some variable load. The dispatch has been calling for them to change their ramping directions quite a bit, which makes optimization hard. But fortunately been able to see some fairly good performance. I can also monitor historical performance relative to what's been going on in real time. The blue dots here are my historical data file. It consists right now of about a year's worth of data. And then the red and the crosshairs show the last hour and current measurements. This is heat rate. Again, you can see how heat rate is starting to decline even as we're ramping up a little bit. Generate similar trends of fuel flow, total air flow in the unit, all relative to historical measurements. And I can also monitor what my emission rates have been doing. So this is CO and ppm, my NOx. This is another representation of NOx. Again, all customized to the needs of the site operators and engineers. If I go now, I'll look at the actual bias control system and how I interface with it. Griffin does all of its work by basing its calculations off of the DCS's set point. So this is the control system's internally calculated value. That's this column right here. And then how Griffin interfaces is it's allowed a positive or a negative and a positive range that it can move that parameter within. And it goes ahead and calculates a bias, which you can see displayed right here. And then determines a final target, and that's really just for display. The bias here is how Griffin implements its results into the system. And what's really cool and useful about the Griffin system is I can go ahead and manipulate any of these ranges in real time without the need to recompile or stop and refresh the system. I can do all that with a functioning live system. All I have to do is interface with these two new screens, double click anything that I would like to manipulate, and come down here and click update. I took away the ability for this to be biased at all, put the ranges to 0. You'll see that that bias will here pretty quickly reflect that after the next cycle of the application. See, the bias goes to 0, and now the Griffin target over here matches the DCS target. And here shortly you'll see the actual feedback of that damper respond as the actuator moves. So this enables us to do rapid prototyping and testing of different configurations of the system. And this is also very useful for unique situations that the unit may find itself in. If we're able, let's say something unique is going on with the unit, we have a strange mill combination or something like that, we can do some rapid testing here by simply changing limits. And then if we find something that's repeatable and useful, in the actual applications, I can come in and develop expert logic to allow that to be an automatic control move. And that's what you're seeing here is the actual logic development space or platform. Again, same thing here. If I want to make changes or manipulations to any of this, all I have to do is make that change. Let's say I want to add a calculation right here. And then you'll see I'm adding it to this logic stream. Live logic is shown in real time. I can see the values of each parameter. I can see the pathway that the logic is taking. You see if there's decisions being made. One side is not lit up, one path while the path that is being executed is. Then I can come in here and do a very simple calculation. Let's do 5 plus 5. And all I have to do to make this a part of the control stream is go and click save and refresh. It'll take a moment to capture that, and then on its next cycle you'll see that that result will show up here and that this execution pathway will become active. And there it is. So there's a result of 10, and now that pathway is active. That again enables us to do that rapid prototyping, that expert knowledge capture, which is extremely useful when you have a number of experienced operators and engineers who may or may not be leaving, retiring at any point. All of the things that you see in here, particularly on how we control things like tilts and other parameters that there's a lot of response to and have a big impact on the unit. We develop all of these types of things by continual interaction with operators and engineers. We take their best practices and we find a way to make them automatic. That results in really stable and repeatable control that overall provides greater consistency and improved performance to the unit. So that really is the bulk of the applications. The sibling application operates the same way. You can see here I can monitor each siblower activation that the unit or that the KSB system engages by each one of these little spikes. Each one identifies a different type of blower, and I can see how each blow impacts final steam temperatures here. All of this is developed again in response to unit circumstances, and the knowledge-based soot-blowing system is exactly that. It's a knowledge-based, rule-activated, and governed system. We have a lot of success with in generalizability and consistent performance. I believe that's probably everything that I'd like to show. Maybe one last thing is just the ability to do calculations in real time and comparisons and analysis. This table here shows how the unit's been performing with the Griffin system engaged and disengaged. See another metric of efficiency, the CO2 emitted per megawatt hour, about a 1.3% improvement with Griffin engaged. And you also see a high service factor of the Griffin system. We can do analysis of how emissions perform during certain ramping situations, up or down, or break those out in any way that is of interest to the unit. A lot of freedom and a lot of flexibility in the things that we can accomplish here, and this is really what makes the Tabor COS and KSB applications extremely effective and a great product for realizing performance improvement at power generation, as well as other process sites such as steel manufacturing, smelters, food processing, chemical processing. Really an agnostic system with the capability to interact with any process with inputs and outputs. Thank you.